Hello everyone, I'm Karen and I'll be talking about acids and bases today. I'm the SI leader for Professor Ding for this quarter. So let's get started. So there are two different definitions for every acid and every base, and that depends on the type of definition. So there's a Lewis definition and Bronsted-Lowry. So for a Lewis definition, an acid accepts lone pairs while a base donates the lone pairs. When I'm talking about lone pairs, I'm saying electrons. So two electrons, which make up a lone pair. However, for Bronsted-Lowry definition, an acid is a proton donor, so it donates a hydrogen, and then bases, they're proton acceptors. You should familiarize yourself with these definitions because questions like this will come up on the exam. So she also talks about formation of complex ions. So complex ions are metal ions, which are Lewis acid, plus ligands, which are Lewis base, will make you a metal complex. So some terminology that we should know is coordinate bonds. So coordinate bonds are covalent bonds that are formed when one ion or molecule donates a pair of electrons to another ion or molecule. And it's an interaction between lone pair and empty orbital, and that's an example of a Lewis acid-base behavior. We should also know what a complex ions mean. An ionic species consisting of a metal ion bonded to one or more Lewis bases. And you should know that ligands are a Lewis base bonded to a central metal ion of a complex ion. This might all sound very weird right now and doesn't make sense, but we'll see a visual in a bit to make everything more clear. So we should know what coordination compounds are. So they are important class of chemical compounds. They're usually made of a metal ion interacting with one or more ligands. And the interaction is called the coordination bond. So lone pairs of electrons from the ligands are donated to the metal center ion. So what we're looking at is a metal center ion with ligands around it. That's basically what this is saying. So for the visual, here we see cobalt in the middle, and we have the water molecules around it. So this is a hydrated ion. We have ligands, which are chlorine here, right? So we go through the reaction, and we have cobalt bound to 4 different chlorines, and you have the water on its own. So the cobalt and the chlorine is called the complex ion. We should also, as we mentioned earlier, the definition of the coordinate bond binding the ligand and the metal ion. So these are the coordinate bonds. So she also gave some examples that were also found in the book of some complex ions. You should know the coordination number equals to the number of ligands. So we have 6 here, we have 4, we have 4 on this side, we have 4 here, and we have 4 and 2 and 2. Hopefully you remember from CHEM001A then what the steric number means, the shapes, and some examples. You should be able to recall the steric number and the shapes easily since you learned it in CHEM1A. As you see here, it says the steric number is 6. However, we have 4 different ligands, and that's because it accounts for the lone pairs. So this has lone pairs. So she also wanted to discuss in lecture a question that came up in discussion that people were struggling with, and it had to do with Rice tables. So I will go over that as well. So it says, what's the equilibrium concentration of copper in a 1.0 molarity solution of copper nitrate given the following information? So it gave you this equation, right? So, and it's balanced for you, and it gave you the equilibrium constant of the forward reaction. So our first step is to set up a Rice table as if it was completely dissociated. So let's take a look. So we have the Rice table, the before, the change, and the after. And I said here, take care of the reaction first and assume that it is a complete reaction, right? So you have 1 mole, 4, and then 0, you subtract the 1, you subtract 1 and 4, and then you add the 1 here, and you get 0, 0, and 1, and that's a complete reaction. The reason we have 1 here and not 4 is because we have a limiting reagent. So now let's set up the second rice table, but this is, we are setting this equilibrium considering the fact that a little amount of the complex product dissociates back to the reactants, since it's a reversible, reaction, right? So we have 0, 0, 1, that's the initial from our, sorry, I'll go back. This is our initial from the final of the last rice table. So you add, it's going in reverse, so you subtract x, you add a number x here, and then 4x and plus x. And remember, these coefficients are from the mole-to-mole ratio. And then our final should be x, 4x, 1 minus x. So as we all know, when we learned a couple of lectures ago, we set up rice tables by doing the concentration of the products over the concentration of the reactants. So if we look here, we have 1 minus x over x times 4x to the 4th because of the coefficient. And we set that equal to the equilibrium constant, which was 5.0 times 10 to the either 16 or 13. I don't remember, but it's in 2 slides back. And basically, if you try to do this normal mathematical way, you're going to find it very complicated because we will have x to the 4th in the equation. So here, since it's x to the 4th, we know x is way less than 1.0. So in this case, x is a negligible number, which we can kind of ignore. So it would be 1.0x is approximately 1. So this numerator would be just 1. And after you do the math, you should get that x is 6.0 times 10 to the negative 4 molarity. So the initial question was asking for the concentration of copper, and copper did not have any coefficients, and it was just x, so this would also be the concentration of copper. So basically, thank you for listening. This is the content for the second lecture for this week. Please let us know if you have any questions on the worksheets, or come to office hours and ask us questions. My office hours are on Tuesday from 1 to 3, and the Zoom link should be in the email I sent previously and in the first video of this series for CHEM001C. Thank you.